A galactic life cycle begins in violence and ends in silence. These massive islands of stars follow a dramatic story written across billions of years, a narrative that holds the key to our universe's ultimate fate. By the end of this journey, you will understand not only how galaxies are born and die, but how their existence shapes the very fabric of reality itself. We will uncover why some galaxies flourish with newborn stars while others fade into red ghosts, and what mysterious force ultimately dictates their final moments. What do you believe is the most profound legacy a galaxy leaves behind? That initial violence of creation left behind a universe that was, for a moment, perfectly uniform. A hot, dense fog of fundamental particles and blinding light filled every corner of existence, a seething plasma where atoms could not yet hold together. In this primordial soup, the very idea of a galaxy was impossible. There were no stars, no planets, no structures of any kind, only a chaotic, expanding fireball. For hundreds of millions of years, the universe remained in this dark age, a profound silence waiting to be broken. The critical change came as the cosmos continued to stretch and cool. The energy of the initial fireball faded, allowing particles to finally combine into the first simple atoms, mostly hydrogen and helium. This transition cleared the cosmic fog, but the universe was still a vast and remarkably empty place. So how did we get from this near-perfect smoothness to the magnificent, structured universe we see today? The answer lies in the faintest of whispers from the very beginning. Incredibly tiny quantum fluctuations, minuscule ripples in the fabric of space-time born in the first fraction of a second, were stretched to enormous sizes during a period of hyper-expansion called inflation. These ripples created tiny variations in density, regions that were ever so slightly denser than their surroundings, and into these subtle wrinkles, an invisible force began to flow. Dark matter, which does not interact with light but feels the pull of gravity, started to gather within these slightly denser patches. Think of it like a hidden scaffolding slowly taking shape in the darkness. This dark matter clumped together, forming a vast, interconnected cosmic web, a network of filaments and nodes spanning the entire observable universe. Within the largest nodes of this web, immense spheres of dark matter, known as halos, began to condense. These halos would become the gravitational anchors, the skeletons upon which the visible universe would be built. Their immense, unseen pull created deep wells in the fabric of space-time, setting the stage for the next great act. The primordial ingredients were now assembled. The cosmic stage, once a formless blaze, was prepared for the first galaxies to step into the light. Then came the first sunrise, a dawn that was not a single event but a slow, cosmic awakening. Across the dark expanse, pockets of pure hydrogen and helium gas, drawn deep into the gravitational wells of those dark matter halos, began to collapse under their own immense weight. The pressure and temperature at their cores skyrocketed until they crossed a threshold never before reached, triggering the first nuclear fusion reactions. The universe for the first time saw stars. These firstborn suns, known as population 3 stars, were unlike any that would follow. They were titans, behemoths hundreds of times more massive than our own sun, and they burned with a ferocious, brilliant blue-white intensity. Their lives were spectacularly short, blazing across the cosmic stage for only a few million years before exploding in violent supernova. Yet their brief existence was utterly transformative. Their intense ultraviolet radiation blasted through the surrounding neutral hydrogen gas, tearing electrons from their atoms in a process called reionization. This great cleansing slowly burned away the cosmic fog, rendering the universe transparent to light for the very first time and ending the billion-year-long dark ages. Within the safety of their dark matter cradles, these first stars did not form in isolation. They were born in clusters, their collective gravity pulling in more and more pristine gas. These were the protogalaxies, the raw, chaotic seeds of future giants. They were not the elegant spirals or smooth ellipticals we recognize today, but rather small, irregular, and turbulent clumps of a few million stars, all swaddled in vast clouds of gas. There was no order, no defined shape, only a frantic, brilliant chaos of birth and death. The explosions of the first massive stars seeded this surrounding gas with the first heavy elements, the forged ashes of stellar furnaces. These elements, carbon, oxygen, iron, would become the building blocks for rocky planets, organic molecules, and eventually, life itself. In this era of first light, the universe was not just waking up, it was learning how to build. It was forging the very tools it would need to create a more complex and diverse cosmic future, setting a foundation upon which everything, including us, would one day stand. From that initial chaos of first light, the universe began a grand construction project. Those small, turbulent protogalaxies were not destined to remain isolated. They were the bricks and mortar for something far greater, drawn together by the relentless pull of gravity in a process known as hierarchical clustering. It is a simple but powerful idea that small things merge to build bigger things. Imagine a cosmic stream where countless tiny tributaries of stars and gas flow together, gradually forming a mighty river. This was the assembly of the galactic building blocks, a process that would define the next several billion years. At the heart of this assembly were the dark matter halos, the invisible skeletons laid down in the early universe. Their immense gravitational pull created deep wells in space-time, acting like cosmic magnets that steadily drew in everything around them. Vast rivers of primordial hydrogen gas, along with smaller satellite galaxies, were funneled into these growing structures. The journey of this gas was not a gentle one. As it spiraled inward, it collided with other streams, creating tremendous shock waves that compressed the gas into dense, swirling clouds. This violent compression was the trigger for starbursts, spectacular fireworks displays of star formation where thousands, even millions of new stars ignited at once. The galaxy was essentially building itself through a series of collisions, each merger adding more stars, more gas, and more dark matter to its growing bulk. It was during this tumultuous era that the universe may have witnessed the birth of its first true monsters, the Quasars. As gas poured into the centers of these emerging galaxies, it fed the supermassive black holes that were forming there. A black hole itself is dark, but the material spiraling into it is not. This infalling gas, compressed and heated to incredible temperatures in a swirling accretion disk, can outshine an entire galaxy, blazing across the cosmos as a quasar. These beacons of intense light served as a regulating force, their powerful radiation and jets sometimes blowing away the very gas that fed them, temporarily halting star formation and shaping the galaxy's growth. Each of these violent mergers did more than just add mass, they sculpted the galaxy's ultimate destiny. A series of gentle, grazing collisions with gas-rich satellites could help build a beautiful, ordered disk, its stars settling into the graceful spiral arms we recognize. In contrast, a major merger between two roughly equal-sized galaxies would completely disrupt such delicate structures, churning the stars into a random, swelling ellipsoid, creating a featureless elliptical galaxy. The diversity we see in the night sky, the stately spirals and the glowing red ellipticals, is a direct result of this long and varied history of collisions and acquisitions. The building blocks were finally coming together, assembling the recognizable islands of stars that would light up the cosmic dark. But these magnificent galactic structures, born from chaos and sculpted by collisions, face a constant threat from within. Every spiral galaxy, including our own Milky Way, spins at tremendous speeds, with stars on its outer edges whirling at hundreds of kilometers per second. According to the laws of physics we understand, this rapid rotation should create a powerful centrifugal force, flinging stars and gas out into the void, tearing the galaxy apart over cosmic time. Yet when we look at the sky, we see galaxies that have remained intact for billions of years. They are not flying to pieces. Something invisible must be holding them together, acting as a cosmic glue. This is the profound and essential role of dark matter. Though we cannot see it, touch it, or directly detect it with our instruments, dark matter is the hidden architect and permanent stabilizer of the galactic world. It is not a minor component. It makes up roughly 85% of all the matter in the universe. Its primary influence comes from the vast spherical halos it forms around every galaxy. These halos extend hundreds of thousands of light years beyond the galaxy's visible edge of stars, creating an immense, unseen gravitational anchor. Think of a galaxy not as an isolated island, but as the brilliant core of a much larger, invisible structure, like a city whose lights you can see, built upon a mountain whose dark bulk lies hidden beneath the surface. This dark matter mountain provides the gravitational pull that counteracts the galaxy's spin, keeping every star in its stable orbit and preventing the entire system from unraveling. The evidence for this is etched into the galaxy's rotation curve, a graph that charts the orbital speeds of stars at different distances from the galactic center. If only visible matter were present, stars on the outskirts should orbit much more slowly, just as Pluto moves more sluggishly around the Sun than Earth does. Instead, we observe that these outer stars whip around just as fast as the inner ones. This flat rotation curve is one of the strongest indicators that an enormous amount of unseen mass, dark matter, is enveloping the entire system. Computer simulations of the universe's evolution paint a stark picture, a universe where dark matter is absent. In those models, the initial density fluctuations from the Big Bang are too weak to overcome the expansion of space. Gas never collapses into dense enough clouds. The first stars struggle to ignite, and those few small clumps of stars that do form are quickly torn apart by their own motion. Without its dark foundation, the universe would remain a dark, formless, and sterile sea of hydrogen, a place where galaxies, stars, planets, and life could never emerge. The properties of a galaxy's dark matter halo, its total mass and its density distribution, directly dictate the galaxy's fate. A massive, dense halo can draw in vast reservoirs of intergalactic gas, fueling star formation for eons. It can also protect the galaxy from external threats, its gravity acting as a shield that deflects or absorbs smaller intruders. The invisible architecture laid down at the dawn of time continues to shape every aspect of a galaxy's life, from its birth in the early universe to its final, silent form. So, why does one galaxy become a graceful, star-forming spiral while its neighbor evolves into a vast, red elliptical? The final shape of a galaxy is not random. It is the direct result of its personal history, a cosmic diary written in the motions of its stars. The key factor is angular momentum, a property that describes how much an object is spinning. Think of a figure skater pulling her arms in to spin faster. That conserved motion is angular momentum. In the early universe, a vast cloud of gas collapsing to form a galaxy possessed a certain amount of this spin. If that spin was significant and the galaxy grew in relative isolation, something beautiful happened. The collapsing gas naturally flattened into a vast, rotating disk, much like a spinning ball of pizza dough stretches out into a flat crust. Within this stable disk, cold gas could settle into dense clouds, providing the fuel for ongoing star formation. This is the origin story of spiral galaxies like our own Milky Way, majestic pinwheels where new stars are continually born in their bright arms. But not all galactic lives are so peaceful. When two spiral galaxies of roughly equal size collide, it is a catastrophic event that completely rewrites their story. Their delicate disks are shredded, their stellar orbits randomized into a chaotic, swelling cloud. The collision drives almost all of their remaining gas into the galactic core, triggering a final, furious burst of star formation called a starburst. This last frenzy uses up the galactic fuel supply in a relatively short time. What remains is a vast, spherical or football-shaped collection of aging stars, a red and dead elliptical galaxy. With no cold gas left to form new stars, its population of stars simply grows older together, their collective light shifting to redder wavelengths over billions of years. Then there are the irregular galaxies, the cosmic rebels that defy easy classification. These are often systems still under construction, or ones that have had a close encounter with a larger neighbor, their shapes stretched and twisted by gravitational tides. They are living snapshots of a galaxy in transition, caught between one state and another. The ultimate fate of any galaxy is therefore shaped by a delicate balance of forces, its initial spin, the violence of its mergers, and even the density of its environment. A galaxy living in a crowded cluster is far more likely to suffer disruptive collisions and become an elliptical, while a galaxy in a quiet cosmic suburb has a better chance of retaining its disk and continuing to form stars. This incredible diversity we see when we look through a telescope is not a collection of different species, but a gallery of different life stages and life stories. Each shape tells a unique tale of birth, growth, and interaction, a permanent record of the events that shaped an island of stars across cosmic time. This constant rhythm of stellar birth and death is the very heartbeat of a galaxy. Deep within the spiral arms of galaxies like our own, vast clouds of cold molecular gas and dust, known as nebulae, drift through the darkness. These are the galactic nurseries, and they are far from peaceful. They are turbulent, chaotic places where pockets of gas, nudged by a passing shockwave or their own gravity, begin to collapse. As a dense knot within a cloud contracts, its internal pressure and temperature soar. When the core becomes hot and dense enough, it crosses a critical threshold, igniting nuclear fusion and giving birth to a new star. This process is not a solitary event. A single collapsing cloud can fragment, creating entire clusters of stars, siblings born from the same cosmic womb. The rate at which a galaxy forges these new stars depends on its internal conditions. A rich reservoir of cold, dense gas leads to a high birth rate, creating a brilliant blue-white galaxy. A galaxy with little cold gas, or where the existing gas is too hot and turbulent to collapse, becomes a quieter, redder place. So what controls this delicate balance between creation and stillness? One of the most important regulators are the spiral arms themselves. They are not fixed structures made of the same stars, but rather majestic density waves that move through the galactic disk like a traffic jam on a highway. As stars and gas clouds orbit the galactic center, they enter a spiral arm where the gravitational pull of the wave compresses them. This squeeze triggers the collapse of gas clouds, lighting up the arms with brilliant young star clusters. The stars then continue on their orbit, leaving the nursery behind, while the wave itself remains, ready to trigger the next generation. But the most dramatic influence comes from the stars themselves, in a process known as feedback. The most massive stars live fast and die young. During their short lives, they blast their surroundings with intense ultraviolet radiation and powerful stellar winds. When they finally explode as supernova, they unleash unimaginable energy. This violence has a dual nature. On one hand, the shock waves from these explosions can slam into nearby gas clouds, compressing them and triggering the birth of more stars. It is a chain reaction of creation. On the other hand, that same energy can heat and disperse the surrounding gas, blowing it away and shutting down star formation in that region for millions of years. It is a self-regulating cycle where starbirth sows the seeds of its own temporary destruction. This eternal dance between creation and dispersal dictates a galaxy's entire life story. A galaxy with strong, continuous feedback will eventually use up or expel its gas reservoir, its star formation slowing to a whisper. This is the path that leads to the red and dead elliptical galaxies. A galaxy that can gently recycle its gas, perhaps by drawing in fresh fuel from intergalactic space, can maintain a steady rhythm of star formation for billions of years, preserving its blue spiral vitality. The appearance of a galaxy, its color and its light, is a direct reflection of this internal cosmic engine, an engine powered by the lives and spectacular deaths of its own stars. This recycling of cosmic material is the galaxy's very metabolism. A galaxy is not a static collection of stars, but a dynamic, breathing entity, continuously processing its raw materials through an intricate cycle of life, death, and rebirth. At the heart of this cycle is the interstellar medium, a vast and diffuse ocean of gas and dust that fills the space between the stars. This is the galaxy's primary reservoir of raw material. When a dense cloud within this ocean collapses to form a star, it is like the galaxy drawing a breath. The star then acts as a giant nuclear furnace, fusing the simple, primordial hydrogen and helium into heavier elements deep within its core, creating carbon, oxygen, nitrogen, and iron. For most of its life, a star hoards these newly forged metals, but in its final death throes, whether in a gentle planetary nebula or a violent supernova explosion, the star exhales, seeding the surrounding interstellar medium with its enriched ashes. This process fundamentally changes the composition of the galactic gas. The next generation of stars that forms from this material will be born with a higher metallicity, a richer blend of heavy elements. Our own Sun is a product of this recycling, a star forged from the remains of countless stellar ancestors that lived and died before it. This chemical enrichment is the single most important factor for the potential of life. Without those previous stellar generations creating and dispersing the elements for rocky planets, water, and complex organic molecules, our solar system, and we ourselves, could never have existed. The galaxy is not a closed system, however. It breathes in and out on a grand scale. Fresh, pristine hydrogen gas steadily rains down upon the galaxy from the intergalactic medium, a slow accretion that provides new fuel for future star formation. At the same time, the intense energy from stellar winds and supernova explosions can drive powerful galactic winds, blowing vast amounts of processed gas right out of the galaxy and back into intergalactic space. This is the galaxy's metabolic balance, a constant tug of war between gas inflow, star formation, and gas outflow. A galaxy that can efficiently draw in fresh gas will thrive, maintaining its star-forming vitality for billions of years. A galaxy where outflows dominate will slowly starve, its star formation rate dwindling as its fuel supply is depleted or blown away. This balance ultimately dictates a galaxy's growth, its color, and its long-term fate. When astronomers look at a galaxy, they can read this entire history in its light. By analyzing the specific signatures of different elements in a star's spectrum, they can determine its metallicity, effectively dating its birth within the galaxy's timeline. Stars in the halo of our Milky Way, for instance, are ancient and metal-poor, relics from a time before many recycling cycles had occurred. Stars in the galactic disk are younger and richer in metals, products of a well-mixed and processed environment. This chemical fingerprint is a permanent record, a story written not in words but in the elemental composition of every star, telling us which generation it belongs to and what the galaxy was like when it was born. The galaxy's metabolism is what transforms it from a simple collection of hydrogen and helium into a complex, chemically rich ecosystem, capable of forging the building blocks of worlds and life. Yet even this intricate metabolic cycle is not the final word in a galaxy's story. There is another, far more powerful engine at work, one capable of shaping a galaxy's destiny from its very core. At the heart of nearly every massive galaxy, including our own Milky Way, lies a supermassive black hole. These are not the dark, passive voids one might imagine. When they feed, they transform into the most powerful and influential objects in the universe. As vast amounts of gas and dust spiral inward, they form a searingly hot, glowing disk around the black hole, an engine known as an active galactic nucleus. This accretion disk shines with the brightness of billions of stars, and in its most extreme form, we call it a quasar. A single quasar can outshine its entire host galaxy, becoming a beacon visible across the cosmos. But this phenomenal light show is more than just a spectacle. It is a fundamental regulatory force. The intense radiation and powerful jets of particles blasting from the active nucleus pour tremendous energy into the surrounding galaxy. This energy heats the vast reservoirs of cold gas, the very fuel for star formation, preventing it from cooling and collapsing into new stars. It is a cosmic feedback loop of breathtaking scale. The more mass the galaxy has, the more gas falls into its center, feeding the black hole and making it more active. The more active the black hole becomes, the more energy it releases, which then heats or even blows away the galactic gas supply, ultimately starving both the black hole and the galaxy itself of new material. This elegant mechanism explains a mysterious connection astronomers have observed: the tight correlation between the mass of a galaxy's central bulge and the mass of its supermassive black hole. They grew up together, each regulating the other's growth. The black hole acts as a built-in governor, preventing the galaxy from becoming too large and disrupting the delicate balance of the cosmic web. During particularly violent feeding phases, these black holes can drive colossal winds that sweep across the galaxy, ejecting its remaining gas into intergalactic space. This is the ultimate act of galactic regulation, a final quenching of star formation that can transition a vibrant, blue spiral into a quiet, red and dead galaxy. Far from being mere destructive monsters, these supermassive black holes are the master architects of galactic ecosystems, their immense power ensuring that no single galaxy can dominate and that the universe maintains its beautiful, structured diversity. This galactic cannibalism is the final, dramatic act of growth. Throughout cosmic history, no large galaxy has grown in complete isolation. They have all been shaped by a relentless dance of collisions and close encounters with their neighbors. When two galaxies of similar size are drawn together by gravity, their initial approach is a slow, graceful ballet spanning hundreds of millions of years. But the final merger is anything but gentle. Their delicate spiral arms are stretched into long, luminous tidal tails, scattering stars across intergalactic space like glitter thrown from a cosmic hand. The real violence, however, happens within the gas. The immense clouds of hydrogen in each galaxy slam into one another, creating tremendous shockwaves that trigger a ferocious firestorm of star birth. This is a starburst, a dazzling but short-lived frenzy where the galaxy can form stars hundreds of times faster than its normal rate, blazing with the light of millions of newborn suns. Simultaneously, vast rivers of gas are driven inward, flooding the galactic core and providing a feast for the supermassive black hole lurking there. This sudden influx can awaken the dormant beast, turning it into a brilliant quasar whose energy can then blast back out and reshape the entire galaxy. Our own Milky Way is a quiet cannibal, its history written in the faint, ghostly streams of stars that wrap around its halo. These stellar streams are the dissolving remains of smaller dwarf galaxies it has consumed over billions of years, their stars torn apart and assimilated into the galactic whole. Computer simulations reveal the ultimate fate of a major merger with stunning clarity. Two beautiful spiral galaxies, each with a distinct disk and graceful arms, will slowly circle each other, their gravitational pull distorting their shapes. Over more than 1 billion years, their stars' orbits are completely randomized, their gas used up in the final starburst or blown away by quasar activity. What finally emerges is no longer a disk, but a smooth, featureless swarm of stars, a red and dead elliptical galaxy. The evidence of this violent past is not just in a galaxy's shape, but in the very motions of its stars. In a spiral galaxy, most stars orbit in an orderly, rotating disk like cars on a racetrack. In an elliptical galaxy born from a merger, the stars move in every direction, a chaotic beehive of orbits with no preferred rotation. This fundamental transformation shows that a galaxy's structure is not permanent. It is a temporary state in a long and dynamic life cycle, constantly rewritten by its interactions with the cosmos around it. 10 billion years ago, the universe hit its prime. This was the era of cosmic noon, a period of unparalleled vitality when the cosmos blazed with the light of its most productive years. Galaxies did not just form stars, they forged them in a frantic, glorious rush, with birth rates tens or even hundreds of times greater than what we see in the modern universe. The sheer abundance of pristine hydrogen gas made this possible. Galaxies were swimming in fuel, their vast reservoirs constantly replenished by thick rivers flowing in from the cosmic web. This was a time of frequent and dramatic interactions, where galactic collisions were not rare catastrophes but regular events, each one triggering new firestorms of star formation and feeding the ravenous black holes at the galactic centers. The collective light from countless newborn stars, massive and blue-white, joined with the searing glare of quasars to flood the cosmos with intense ultraviolet radiation. This great bath of energy ensured that the hydrogen between galaxies remained ionized, keeping the universal highways transparent and charged. It was during this brilliant, hyperactive crescendo that the universe forged the majority of the stars we see today. The massive central bulges of modern galaxies were largely assembled, and the supermassive black holes at their hearts achieved most of their final mass, gorging on the plentiful gas of that fertile time. This period represents the maturation of the cosmic landscape, the point at which the universe, having built its grand structures, filled them with light and activity. The legacy of cosmic noon is written into the very fabric of every large galaxy we observe. The ancient, red stars that dominate the bulges of spirals and the entire populations of elliptical galaxies are the silent survivors of that bygone age of fire. They are the living memory of a universe in its glorious, tumultuous youth. But that brilliant era of cosmic noon could not last forever. The frantic pace of star formation began to slow, and across the universe, a great quenching settled over countless galaxies. This was not an extinction event, but a transition, a shift from vibrant youth to a quieter maturity. Many galaxies simply ran out of fuel. After billions of years of furious star birth, their vast reservoirs of cold gas were depleted, used up in the creation of generations of stars. With no fresh material to collapse into new suns, the star formation rate plummeted, and the galaxy's brilliant blue light faded to a softer red. Other galaxies experienced a different kind of stillness, known as morphological quenching. In a galaxy with a large, stable central bulge, the gravitational environment becomes so orderly and calm that the remaining gas clouds cannot collapse. The very stability that protects the galaxy also prevents new stars from being born, like a sea so calm it cannot form a wave. Yet the most dramatic quenching mechanism comes from within. The supermassive black hole at the galaxy's heart, once fed by mergers, can unleash tremendous energy. As it feeds, it drives powerful winds and floods the galaxy with radiation, heating the galactic gas to such high temperatures that it can no longer cool down and form stars. In extreme cases, these active galactic nuclei can blow the gas clean out of the galaxy, permanently cutting off its star-forming fuel supply. Enrichment seals the fate of many galaxies as well. A spiral galaxy drifting into a dense cluster faces a cosmic ordeal. The immense pressure of the hot gas that permeates the cluster acts like a relentless gale, stripping the galaxy of its own gas reservoir in a process called ram pressure stripping. It is like driving a car through a torrential downpour with the windows open. The interior is swiftly cleaned out. Alternatively, a galaxy can be strangled, its supply of fresh intergalactic gas cut off as it falls into the cluster, leaving it to slowly consume its remaining fuel with no way to replenish it. This great quenching is written in the most fundamental division we see in the night sky, the color bimodality of galaxies. On one side are the blue galaxies, alive with the light of young, massive stars and active nurseries. On the other are the red galaxies, dominated by the older, cooler stars of a population that is aging together. This is not a random assortment. It is a clear signature of a galaxy's position in its life cycle. The transition from blue to red marks a critical turning point, the moment a galaxy's internal engine of creation finally stills, and it begins its long, slow journey into a different kind of existence. The vibrant blue light of a youthful galaxy does not last. It is a fleeting signature of a specific kind of life, the brilliant but brief existence of massive stars. These blue giants are the cosmic equivalent of mayflies, living for only a few million years before exploding in spectacular supernova. When they are gone, they leave behind a stellar population that is quieter, cooler, and far more enduring. The galaxy's overall color slowly shifts from a brilliant blue-white to a softer, golden yellow, and finally to a deep crimson red. This changing hue is not merely an aesthetic shift, it is the most fundamental readout of a galaxy's life story, a direct indicator of the average age of its stellar citizens. A blue galaxy is one still buzzing with the energy of newborn suns, while a red galaxy is a retirement community for ancient stars, a place where star formation has long since ceased. The light we see from a distant galaxy is therefore an integrated message, a blended signal from billions of individual stars. Astronomers can dissect this light, breaking it down into its constituent colors through a spectrum to read this galactic biography. They can determine not just the current population, but also trace the history of past generations. the chemical fingerprints within the starlight reveal a continuous process of enrichment. Each generation of stars fuses heavier elements in its core and, upon its death, scatters these metallic ashes back into the interstellar medium. The next generation of stars then forms from this richer material. A star's metallicity, its abundance of elements heavier than helium, acts as a cosmic clock, telling us when it was born relative to the galaxy's history. The oldest stars found in the galactic halo or in globular clusters are metal-poor, relics from a time before many cycles of stellar life and death had occurred. The younger stars in the disk are metal-rich, products of a well-mixed and recycled environment. This relentless aging process is the ultimate fate of every galaxy's stellar population. As the massive blue stars wink out and are not replaced, the collective light becomes dominated by the long-lived red dwarfs and aging red giants. The galaxy transforms from a blue, gas-rich system, actively building new worlds, into a red, gas-poor system, its future dictated solely by the slow, steady burning of its oldest stars. The color of a galaxy is its final confession, revealing whether it is in the spring of its life, ablaze with youth, or has settled into a deep and permanent autumn. The quiet, steady burning of a galaxy's stars is only half of its story. The other half is written in the neighborhood it calls home. A galaxy does not evolve in a vacuum. Its destiny is profoundly shaped by the immense cosmic structures it inhabits, from the sparse voids to the crowded, violent heart of galaxy clusters. The single most important factor is the local density of galaxies, a simple metric that creates wildly different life paths. In the sparse cosmic countryside known as the field, a spiral galaxy can live a relatively peaceful existence. Here, it can hold onto its vast reservoirs of cold gas for billions of years, spinning gracefully and forming new stars at a leisurely, sustainable pace. Its story is one of isolated self-regulation, but the fate of a galaxy that falls into a dense cluster is entirely different. It enters a realm of extreme gravitational forces and searing temperatures, an environment that can rapidly and brutally alter its fundamental nature. One of the most dramatic mechanisms is ram pressure stripping. As a spiral galaxy plows through the incredibly hot, thin plasma that fills a galaxy cluster, it experiences a cosmic wind of immense force. This wind acts like a torrential gale, and it can literally blow the galaxy's gas clean out of its disk. The stars, held tight by gravity, remain unharmed, but the lifeblood of the galaxy, its star-forming fuel, is stripped away. The result is an anemic spiral, a galaxy that still looks like a pinwheel but has lost its ability to create new stars, its arms growing faint and ghostly. In more extreme cases, the galaxy is transformed into a lenticular galaxy, a strange hybrid that possesses a central bulge and a disk, but with no spiral structure and almost no gas or ongoing star formation. It is a galaxy caught in a suspended state, a fossil of its former self. Beyond this direct stripping, the cluster environment subjects galaxies to a relentless process known as harassment. This involves countless high-speed, close encounters with other cluster members. These gravitational flybys are not slow, merging dances, but rapid tugs that can pull and stretch a galaxy, distorting its beautiful spiral arms, heating its stellar disk, and driving its remaining gas inward to be consumed in a final burst of activity. Over time, this persistent harassment can completely disrupt a galaxy's delicate structure, randomizing the orbits of its stars and transforming it from an ordered spiral into a smooth, featureless elliptical. This is why we observe the powerful morphology-density relation, a clear rule of cosmic geography. In the dense cores of rich clusters, elliptical and lenticular galaxies overwhelmingly dominate. Their red, aging starlight is a testament to a harsh environmental history. Meanwhile, in the lower density outskirts and the field, vibrant blue spiral galaxies are the norm. Two galaxies born identical, with the same mass and the same initial gas supply, can end their lives looking completely different, one a red giant and the other a blue pinwheel, simply because of the cosmic zip code they happen to occupy. The invisible architecture of the cosmic web, with its dense clusters, long filaments, and empty voids, is not just a backdrop. It is an active participant in writing the life story of every single galaxy, guiding its evolution from birth to its final, silent form. Even as we map the grand narrative of galactic life and death, the cosmos continues to unveil profound mysteries. Among the most puzzling are the ghost galaxies, known officially as ultra-diffuse galaxies. These cosmic phantoms possess the sheer physical size of a massive spiral like the Milky Way, yet they contain only a tiny fraction of the stars, perhaps just 1% of the total. This makes them incredibly faint, their light smeared across such a vast area that they nearly disappear against the blackness of space, which is why they have only recently been discovered in significant numbers. How can a structure so large and apparently so fragile hold itself together? The answer, as with so much in the galactic story, seems to lie with dark matter, but in ways that defy simple explanation. Some of these ghostly giants are found to be dominated by it, their expansive forms held together by an immense but invisible mass, like a city-sized balloon filled with lead. Yet, in a twist that challenges our fundamental models, other ultra-diffuse galaxies appear to have almost no dark matter at all. They are just vast, thin clouds of stars, seemingly defying gravity's need for a hidden anchor. Their very existence in hostile environments is another layer of the puzzle. Astronomers have found these wispy structures surviving intact within the violent cores of dense galaxy clusters, places where gravitational tides should have ripped them to shreds billions of years ago. It is as if a delicate soap bubble could float unscathed through a hurricane. This remarkable survival suggests either that these galaxies are incredibly dense with dark matter, making them far tougher than they look, or that our understanding of how tidal forces work in clusters needs revision. Each possibility opens a new door in astrophysics. The dark matter-rich versions might be perfect laboratories for studying this elusive substance in isolation, free from the complicating glare of many stars. The ones lacking dark matter could be even more valuable, offering a pristine test of how gravity and Newton's laws behave on galactic scales without the confounding influence of unseen mass. The discovery of ultra-diffuse galaxies forces a humbling realization that the universe may have more ways of building a galaxy than we ever dreamed. They are not merely faint curiosities, but stark reminders that our catalogue of cosmic structures is still incomplete, hinting at entire chapters of galactic evolution we have only just begun to read. Every star in the night sky is a historian, its light carrying a permanent record of the galaxy's ancient past. We can read this history through galactic archaeology, a science that deciphers the life story of a galaxy by studying its individual stars, much like an archaeologist reconstructs a lost civilization from scattered artifacts and ruins. The key to this cosmic record lies in a star's chemical composition, its unique elemental fingerprint. When a star forms, it locks in the chemical makeup of the surrounding gas cloud, preserving a snapshot of the interstellar medium at that exact moment in cosmic time. A star born early in the galaxy's history, from pristine gas that had been enriched by only a few generations of supernova, will be metal poor, containing only trace amounts of elements heavier than hydrogen and helium. A star born billions of years later, from gas that has been cycled through many stellar life cycles, will be metal-rich, its composition reflecting a long history of cosmic recycling. By measuring the metallicity of thousands upon thousands of stars, astronomers can create a detailed timeline of the galaxy's chemical evolution, charting its growth from a simple, primordial state to the complex ecosystem we see today. The structure of the galaxy itself reveals different chapters of this story. In our own Milky Way, the ancient, metal-poor stars that form the spherical halo are the galaxy's first citizens, relics from a violent epoch of rapid mergers and chaotic assembly. Their random, plunging orbits are a frozen record of that turbulent youth. In stark contrast, the younger, metal-rich stars of the galactic disk orbit in an orderly, thin plane, their circular paths telling a later story of stable, quiet growth after the major mergers had subsided. The most dramatic evidence of past violence is written in the halo itself, where faint rivers of stars known as stellar streams wrap around the galaxy. These are the dissolving remains of smaller satellite galaxies that were torn apart and consumed by the Milky Way's gravity, their stars now assimilated into the galactic halo, leaving behind ghostly trails that trace their final orbits. By mapping the motions and chemistries of these different stellar populations, we can effectively rewind the cosmic clock. We can identify which stars are native to the original protogalaxy and which are immigrants from later acquisitions. We can pinpoint when major merger events occurred and how they contributed to the galaxy's growth, building a detailed family tree of our galactic home. This powerful approach transforms a static image of a galaxy into a dynamic biography, allowing us to witness its entire life story, from its first chaotic beginnings to its current majestic form, written in the ancient light of its countless suns. There is another, invisible architect shaping the galaxy's destiny, a force woven through the void between the stars. Galactic magnetic fields, though unseen, exert a profound influence on nearly every process within a galaxy's ecosystem. These fields begin as incredibly weak primordial seeds, relics from the universe's earliest moments. Over billions of years, they are amplified to immense strengths by a powerful dynamo process, driven by the differential rotation of the galaxy and the churning turbulence from supernova. It is a self-sustaining engine, turning the galaxy's raw motion into a pervasive magnetic presence. This invisible framework does not halt the galaxy's life cycle, but rather guides and regulates it. Within the dark molecular clouds that birth new stars, magnetic fields provide a crucial form of support. They act like a gentle, pervasive pressure, pushing back against the relentless pull of gravity and slowing the collapse of gas. This magnetic resistance influences how a cloud fragments, determining whether it will give birth to a few massive stars or a whole cluster of smaller ones. The very initial mass function of stars, the blueprint for a stellar population, is subtly shaped by this unseen hand. Magnetic fields also serve as the galaxy's transportation network. They channel and confine high-energy cosmic rays, the subatomic particles accelerated by stellar explosions, guiding them along vast, invisible highways. These fields contribute to the overall pressure balance of the interstellar medium, helping to sculpt the bubbles and voids blown by stellar winds. Even the shock waves from supernova, which can trigger or quench star formation, propagate differently under the influence of this magnetic fabric. In majestic spiral galaxies like our own, the fields become remarkably ordered, tracing the spiral arms with stunning fidelity. Their lines of force follow the grand design, sometimes stretching far beyond the visible disk deep into the galactic halo, creating a magnetic corona that we are only beginning to map. Understanding galactic magnetism is more than a niche study. It is a window into fundamental physics and the intricate workings of interstellar space. These fields are a testament to the complex, interconnected ecology of a galaxy. an invisible force that works in concert with gravity and radiation to write the final story of stellar birth, life, and the ultimate fate of these cosmic islands. The brilliant firestorm of cosmic noon is fading into a gentle, distant ember. Across the cosmos, the universe's capacity to create new stars is in a long, slow decline. The frantic construction yard of the past is giving way to a quieter, more settled era, a transition from a universe of vibrant birth to one of enduring maturity. This shift is driven by a simple but profound shortage of raw materials. The intergalactic medium, the vast reservoir of pristine hydrogen gas from which galaxies draw their breath, is becoming more diffuse as the universe expands. Think of it as a great cosmic ocean slowly evaporating, its waters thinning out until only scattered pools remain. Fewer rivers of fresh gas are flowing into galaxies, and the internal reservoirs they have relied on for billions of years are being steadily depleted. Existing gas is either being locked away in long-lived stars, blown into the void by supernova winds and active black holes, or heated to such extremes that it can no longer cool and collapse. The current rate of star formation across the universe is a mere fraction of its glorious peak, just a few % of what it was 10 billion years ago. Based on the trajectory we observe, astronomers project this decline will continue for tens of billions of years into the future. The character of the stellar population will change as well. The universe will no longer be dominated by brilliant, short-lived blue giants. Instead, the most common stars will be small, cool, and incredibly frugal red dwarfs. These diminutive suns can burn their hydrogen fuel for trillions of years, far longer than the current age of the universe. They will become the silent, steady sentinels of the cosmic future, their faint red light persisting long after the last great stellar nurseries have gone dark. This is not an ending, but a fundamental change of phase for the cosmos, a gradual winding down of its most energetic chapter as it settles into a long and stable autumn. The final chapter of a galaxy's life is not a single, universal event. Its ultimate destiny is a deeply personal story, written by its own mass, its environment, and the very shape it has carried for billions of years. A massive elliptical galaxy, resting at the heart of a rich cluster, has already faced its greatest upheavals. Its violent merger-filled youth is far behind it, and it now exists as a stable, aging swarm of stars. For trillions of years, it will simply persist, a cosmic retirement community where stars burn through their fuel at a leisurely pace. There will be no new births to brighten its core, only the slow, steady dimming of its ancient population as star after star reaches the end of its life, leaving behind faint white dwarfs, neutron stars, and black holes. This is a quiet, drawn-out ending, a fading ember in the cosmic dark. In stark contrast, the fate of a beautiful spiral galaxy is far less certain. Its graceful structure is its greatest vulnerability. If it remains in a quiet cosmic backwater, it might continue its gentle spin for eons, its star formation rate gradually slowing as it exhausts its internal gas reserves. But if it is drawn into a dense cluster, its experience will be brutal. The searing plasma between galaxies can strip it of its gas in a cosmic instant, leaving behind a ghostly, star-forming skeleton. A close encounter or merger with another large galaxy can shatter its delicate disk entirely, violently transforming it into an elliptical and bringing its story of ongoing creation to an abrupt halt. The smallest galaxies, the dwarfs, face the most dramatic endings of all. They are the cosmic minnows swimming among whales. A close pass by a giant neighbor can stretch them into long, dissolving streams of stars, their identity completely erased by gravitational tides. Their faint gravitational grip is often too weak to hold onto their own gas, which can be blown away by the collective radiation of just a few massive stars, leaving them frozen in time, unable to create new suns. An isolated galaxy floating in the vast emptiness of a cosmic void may have the most peaceful end of all. With no neighbors to disrupt it and no cluster environment to strip it, it will simply use its gas supply slowly and methodically. Its spiral arms will gradually fade as the last of its stellar nurseries close, and it will transition into a red, quiet disk, its stars aging in unison until the final lights wink out. This incredible diversity of endings, from violent disruption to peaceful exhaustion, mirrors the rich diversity of life we see across the cosmos. Each galaxy's path to silence is a unique reflection of the events that shaped it, a final signature on a biography written across billions of years. The first death of a galaxy is not a violent explosion, but a slow, quiet fading. It begins when a galaxy simply runs out of breath, its interstellar gas supply finally exhausted. This is the most common end, a gradual transition from a vibrant, star-forming ecosystem to a quiescent, aging stellar community. The immediate consequence is a profound silence that falls over the galactic nurseries. With no cold, dense gas left to collapse, the brilliant blue light of massive, newborn stars vanishes from the spectrum. These stellar giants, the mayflies of the cosmos, complete their short, spectacular lives and are not replaced. The galaxy's collective color, once a brilliant blue-white, slowly softens to a golden yellow and then deepens into a permanent crimson red. This red hue is the unmistakable signature of a geriatric stellar population, dominated by the long, slow burning of ancient suns and the cool glow of red giants. The galaxy's light becomes a monologue of old stars with no young voices left to interrupt. This shift in color marks a fundamental and irreversible change in the galaxy's very nature. It is no longer a creative engine, but a passive collection of aging suns, the great cycle of chemical enrichment, which for billions of years forged heavy elements in stellar cores and scattered them back into space through supernova, grinds to a complete halt. No new supernova erupt to seed the void with the ashes of stellar furnaces. The interstellar medium, once a dynamic ocean of potential, becomes a near-perfect vacuum, its composition frozen in time. The galaxy's future is now chemically sealed, its potential for building new generations of rocky planets or complex molecules forever closed. Yet, even in this stillness, a subtle form of evolution continues. Through a process called two-body relaxation, stars gradually exchange energy through their mutual gravitational tugs, like a vast crowd slowly shifting its weight. Over eons, this can lead to a gentle redistribution of stars within the galaxy, causing its core to contract slightly while its outer regions slowly expand. Some stars may even be ejected entirely into the intergalactic void, a slow evaporation of the galactic population, but these are quiet, internal adjustments. There is no renewal, no fresh infusion of energy or material. The galaxy has entered a long cosmic autumn, where its story is no longer one of birth and creation, but of endurance and gradual dimming. This quiet fading is the destiny awaiting countless galaxies across the universe, a final, gentle sigh after an era of brilliant light. For galaxies that wander too close to a gravitational giant, the end is not a quiet fade but a spectacular unraveling. This is the realm of tidal forces, an invisible but relentless power that can tear a galaxy apart without a single direct collision. When two galaxies have a close encounter, the difference in gravitational pull on the near and far sides of the smaller galaxy creates an immense stretching effect. It is a cosmic tug of war that the smaller system cannot hope to win. The result is a breathtaking but destructive spectacle, as long, graceful streams of stars are pulled from the galaxy's outer regions, flung into intergalactic space like glittering scarves. These are the tidal tails, luminous signatures of a galaxy being slowly dismantled. For a small dwarf galaxy venturing near a massive spiral like our Milky Way, the outcome is almost always complete dissolution. Its stars are gradually stripped away, pulled into elongated orbits that eventually dissolve, adding their light to the larger galaxy's halo in a faint, glowing fog. This diffuse starlight, known as intracluster light, is the ghostly residue of countless such galactic meals, a permanent memorial to smaller systems that were consumed long ago. Even for galaxies of similar size, a close pass can be transformative. The delicate gravitational balance that maintains spiral arms can be fatally disrupted, their beautiful symmetry warped into chaotic, irregular shapes. These gravitational encounters act as a relentless sculptor in dense galactic neighborhoods, continually reshaping structures and redistributing stellar populations. It is a slow-motion demolition where the primary tool is not impact, but the invisible, inexorable pull of gravity itself, rewriting the architecture of entire systems over billions of years. Even as individual galaxies age and fade, the vast metropolises they inhabit continue their own epic evolution. Galaxy clusters, the largest gravitationally bound structures in the universe, are living entities in their own right, constantly growing and reshaping themselves. Their primary method of growth is a relentless hierarchical cannibalism. Just as small protogalaxies merge to build the first large galaxies, entire galaxy groups and smaller clusters are now being consumed by these colossal giants. The largest clusters we observe today are still actively forming through these monumental mergers, events so powerful they ripple the very fabric of space-time and heat the gas between galaxies to millions of degrees. Within these dense urban centers of the cosmos, a galaxy's fate is accelerated dramatically. The very environment acts as a crucible forging rapid change. The same processes that gently nudge a field galaxy toward quietude over billions of years are intensified and compressed here. Ram pressure stripping becomes a relentless gale. Harassment from countless close encounters randomizes stellar orbits with stunning speed, and the slow trickle of fresh gas is completely cut off. This environment efficiently and ruthlessly quenches star formation, pushing galaxies toward their red and dead states far sooner than their isolated cousins. The ultimate endgame for a rich cluster is a profound consolidation of power. Through a process known as dynamical friction, the orbits of the largest galaxies within the cluster slowly decay, drawing them inexorably toward the gravitational center. Over hundreds of billions of years, these dominant galaxies will merge one by one into a single monstrous entity. Astronomers call this final act galactic cannibalism, and it results in the formation of a brightest cluster galaxy, a behemoth elliptical that sits alone at the heart of the cluster, having consumed its brightest neighbors. Meanwhile, the space between the galaxies tells its own story of cosmic recycling. The intracluster medium, that searingly hot plasma, becomes enriched with the heavy elements forged in the hearts of countless stars. These metals, ejected over eons by supernova winds and the powerful outflows from active galactic nuclei, are now dispersed on a truly intergalactic scale. This enriched gas is the final testament to the trillions of stellar lives that burned within the cluster, their legacy permanently etched into its hot atmosphere. Long after every constituent galaxy has completed its own life cycle and faded to darkness, the cluster itself continues to evolve, a vast gravitational engine whose slow, stately dance will continue for time spans that dwarf the current age of the universe. Yet even this immense gravitational landscape is not the final word. A deeper, more mysterious force is now writing the next chapter of our cosmic story, one that will ultimately erase the grandest structures from the sky. This force is dark energy, an enigmatic pressure inherent to the fabric of space itself that is causing the universe's expansion to accelerate. For billions of years, gravity had the upper hand, tirelessly pulling matter together to build galaxies, clusters, and the great cosmic web. But around 5 billion years ago, a fundamental shift occurred. As the universe grew larger and more diffuse, dark energy's repulsive effect began to overwhelm gravity's attractive pull. This marked the end of cosmic construction on the largest scales. The great gravitational collapse that built every structure we see has effectively ceased. No new superclusters will ever form, and the cosmic web we observe today is the final, frozen architecture of the universe. For individual galaxies, this accelerating expansion creates a profound and growing isolation. Any galaxy not already locked in a tight gravitational embrace with its neighbors, like those within our own local group, is facing an inexorable future of solitude. The space between these unbound galaxy groups is stretching at an ever-increasing rate, pushing them apart like dots on an inflating balloon. Over time, this expansion will reach a critical and startling conclusion. The light from all galaxies outside our immediate local family will become so stretched and diminished by the frantic expansion of space that their wavelengths will shift beyond the detectable range, effectively disappearing from our view. Eventually, the expansion will become so rapid that their light can no longer reach us at all, as the space between us expands faster than the light can travel through it. They will cross beyond our cosmic horizon, vanishing from the observable universe as if they never existed. The night sky for any future astronomers in our local group will be profoundly empty, containing only the merged stars of Andromeda and the Milky Way, a single island in an endless black sea. Dark energy, which makes up about 70% of the universe's total energy budget, is therefore the ultimate backdrop against which every galactic life cycle now plays out. It dictates the final stage of cosmic evolution, not through violent ends for individual galaxies, but through a silent, inexorable dissolution of the connections between them. It is the force that will ensure the universe's grand narrative of structure and growth concludes not with a bang, but with a quiet, irreversible drift into isolation. The final light in a galaxy does not simply dim, it transforms. As star formation ceases and the last brilliant blue giants vanish, the galaxy's story continues through the slow, stately evolution of its remaining stellar citizens. Each star embarks on its own final journey, a path determined by its birth mass. The most massive stars, those true titans, conclude their brief lives in the most spectacular fashion. They explode as supernova, forging elements heavier than iron in their final, violent moments before collapsing inward. What they leave behind are the densest objects in the universe, city-sized neutron stars with the mass of a sun, or the ultimate gravitational traps, stellar mass black holes. These remnants become the dark anchors of the future galaxy, silent and immensely dense. For stars like our own sun, the end is less dramatic but no less final. After billions of years of stable burning, they swell into red giants, their outer layers gently drifting away to form beautiful planetary nebulae, glowing shrouds of gas that briefly illuminate the darkness. All that remains is a white dwarf, an Earth-sized sphere of degenerate matter that will slowly cool over trillions of years, fading from white to red to a final, cold black cinder. This is the fate of the vast majority of stars in a galaxy. Yet the true long-distance runners are the faint, cool red dwarfs, comprising the most common stellar type. These frugal stars burn their hydrogen fuel so slowly that their lifespans stretch for trillions of years. Long after every other light has gone out, the persistent red glow of these diminutive suns will be the final beacons in the cosmic night. The galaxy's structure itself begins to unravel through internal dynamics. Through countless subtle gravitational interactions, a process known as two-body relaxation slowly redistributes energy among the stars. Some gain enough velocity to be flung entirely free of the galaxy's grasp, ejected into the profound blackness of intergalactic space to wander as solitary suns. Conversely, dynamical friction causes other stars, particularly the most massive remnants, to slowly lose energy and spiral inward toward the galactic core, further concentrating mass at the center. Over near incomprehensible timescales, the galaxy's composition undergoes a fundamental shift. It transitions from a vibrant community dominated by hydrogen-burning stars to a ghostly graveyard populated by stellar remnants, a collection of dark, dense objects and the enduring embers of the last red dwarfs. This silent, internal metamorphosis is the true final chapter of a galaxy's life, a slow transition from a world of light to one of memory and mass. 20 trillion years from now, the stellar fires that once defined the cosmos will be almost entirely extinguished. Galaxies will enter their final active phase, a period dominated not by living stars but by their remains. These are degenerate objects, the final, dense cinders left over after nuclear fusion has ceased. The galaxy's population will consist of three primary relics: white dwarfs, neutron stars, and black holes. White dwarfs, the Earth-sized cores of Sun-like stars, will be the most common. They will no longer generate energy, instead slowly radiating away their residual heat over timescales so vast they defy comprehension. As they cool, these spheres of crystallized carbon and oxygen will fade from a faint red glow to complete blackness, becoming cold, dark black dwarfs. The galaxy will be filled with these invisible, frozen orbs, yet even in this profound darkness there will be occasional rebirth. Very rarely, the gravitational dance of failed stars known as brown dwarfs or the slow spiral of two white dwarfs will lead to a collision. This violent merger can, for a brief moment, reignite fusion, triggering a late-time supernova or even forming a new, short-lived star in what is poetically called a Renaissance event. These isolated flashes will be the last fireworks in the cosmic night, fleeting reminders of the galaxy's brilliant past. Meanwhile, the silent dynamics of gravity continue their work. Through the emission of gravitational waves, pairs of neutron stars or black holes will slowly lose orbital energy, spiraling inward until they merge in a flash of invisible ripples through space-time. Other stellar remnants will be gravitationally slingshotted out of the galaxy entirely, ejected into the intergalactic void to wander forever as dark, solitary nomads. The slow, steady accretion of these remnants by the supermassive black hole at the galactic center will provide its final meals. The galaxy thus transforms into a dark, slowly evaporating collection of degenerate matter, its story punctuated only by the rare, random flash from a celestial event that briefly and beautifully breaks the silence. The final dimming of starlight is not the galaxy's last chapter. Over trillions of years, the very structure of a galaxy begins to erode from within, its stars and remnants slowly escaping their gravitational home. This gradual evaporation is driven by a subtle but relentless process known as two-body relaxation. Through countless gentle gravitational nudges as stars pass near one another, energy is steadily traded across the stellar population. Most of these encounters are minor, but their collective effect is profound. Each interaction is like a slow, cosmic game of billiards where stars exchange tiny amounts of momentum. Over eons, some stars near the galaxy's edge gain just enough velocity to achieve escape velocity, drifting away from the galactic community forever to become isolated wanderers in the void. This stellar evaporation is dramatically accelerated by close encounters with massive objects. A star passing near a dense molecular cloud or a stellar mass black hole can receive a powerful gravitational slingshot, a kick that propels it out of the galaxy entirely. These events act as a natural selection process where the slow and steady loss of members gradually thins out the galactic population, causing the entire structure to slowly expand and lose its cohesive form. On even more immense timescales, another force takes over, the quiet whisper of gravitational radiation. For any two objects orbiting one another, be they binary white dwarfs, neutron stars, or stars circling the central supermassive black hole, their motion creates ripples in space-time that carry away orbital energy. This loss is minuscule, but over quadrillions of years, it causes their orbits to steadily decay, drawing them on an inexorable spiral inward toward the galactic center. This slow in-spiral represents a final consolidation of mass, a relentless drain that pulls the galaxy's densest remnants into its dark heart. While these processes operate on timescales that dwarf the current age of the universe, their conclusion is inevitable in a cosmos with no end. No galaxy, regardless of its initial mass or stability, is a permanent island. Each is a temporary structure in a slow-motion cascade of dissolution, its magnificent form destined to eventually disperse, leaving behind only a darker, simpler cosmos in its wake. But the silent galaxy of stellar remnants is still built from matter, and even matter itself may not be eternal. If the predictions of some grand unified theories of physics are correct, then the very protons at the heart of every atom carry a hidden expiration date. This process, known as proton decay, would mark the final, fundamental transformation of all normal matter in the universe. With an estimated half-life of 10 to the 34 years, a timescale so vast it defies human comprehension, protons would not be stable forever. One by one, over these unimaginable eons, the protons that form the building blocks of every white dwarf, every neutron star, and every last frozen planet would spontaneously decay. They would break down into a shower of lighter particles, positrons, neutrinos, and photons, effectively dissolving into pure energy and radiation. Imagine the slow, inevitable fading of a photograph left in the sun, but on a scale encompassing every celestial structure. The dense white dwarfs and neutron stars, the last enduring monuments to stellar lives, would not simply cool, they would gradually evaporate. Their mass would be converted into a faint, ephemeral glow, a cloud of elementary particles slowly dispersing into the void. This process would systematically dismantle every physical object that once defined a galaxy, leaving behind no asteroids, no planets, and no stellar cinders. The only structures immune to this ultimate dissolution would be black holes. Whatever matter has crossed their event horizons is forever isolated from the rest of the universe, its protons shielded from decay by the profound physics of the singularity. A galaxy would thus be stripped to its most basic components, transforming from a collection of tangible matter into a fleeting, invisible haze of radiation and leptons. This represents the definitive end of the galactic form as we understand it, a final transition where even the atoms themselves surrender to the relentless flow of time, leaving behind a cosmos where only gravity and light remain. These silent galaxies of dark remnants are not the final stage. After the last white dwarf has cooled to black and the final proton has decayed, the universe will enter its longest and most stable era, governed by a single type of object. Supermassive black holes will become the universe's permanent residence, the final structural components of what were once galaxies. Freed from the chaotic dance of stars and gas, these cosmic titans will drift through the void, their immense gravity forming the sole anchor points in an otherwise empty expanse. A former galaxy will no longer be a bright pinwheel or a red swarm, but a diffuse, dark cluster of these gravitational behemoths, all orbiting a common center of mass in a slow, stately dance that will continue for eons. Their growth, once fueled by voracious feasts of gas, will slow to an almost imperceptible trickle. They will incrementally gain mass by sweeping up the ever-diffused dark matter that permeates their space and by capturing the rare, wandering stellar mass black hole or other dark remnant that passes too close. Yet, even these ultimate cosmic structures are not truly permanent. Through a subtle quantum process at their boundaries known as Hawking radiation, black holes slowly lose mass, evaporating over timescales so vast they challenge comprehension. A black hole with the mass of our Sun would take 10 to the 67th years to dissipate, a number with 67 digits. The supermassive black holes at the hearts of galaxies, weighing billions of solar masses, will endure far longer, potentially persisting for up to 10 to the 100 years. This period, the era of black hole dominance, represents the final simplification of cosmic structure. The vibrant, complex ecosystems of stars, planets, and nebulae are reduced to their most fundamental gravitational essence. The black hole is the final, minimalist chapter in the life story of a galaxy, a dark and silent monument to the gravitational force that shaped it from the very beginning. Even the mightiest black holes are not eternal. According to the strange rules of quantum mechanics, the event horizon, that point of no return, is not a perfect barrier. Pairs of virtual particles constantly flicker in and out of existence at the very edge of this boundary. Occasionally, one particle falls in while the other escapes, stealing a tiny amount of the black hole's mass in the process. This is Hawking radiation, a faint whisper of energy that causes the black hole to slowly, imperceptibly evaporate. For a supermassive black hole, this process is so lethargic it is almost frozen in time. It would take a timescale with over 90 digits to completely evaporate, a number so vast it has no meaningful comparison to any human concept of time. Yet, as the black hole loses mass, a remarkable feedback loop begins. The smaller it gets, the hotter it becomes, and the faster it radiates away its remaining substance. The final moments of this evaporation are not a quiet fade. When the black hole's mass dwindles to that of a small mountain, the process accelerates into a runaway cascade, culminating in a final, brilliant flash of high-energy gamma rays, a last testament to its existence. This final burst marks the dissolution of the last enduring structure from the primordial galaxy. The supermassive black hole, the ultimate gravitational anchor that once governed an entire island of stars, simply vanishes. What was once a brilliant pinwheel of billions of suns, then a dark cluster of stellar remnants, and finally a solitary gravitational titan, is now reduced to a diffuse cloud of elementary particles and radiation, drifting in an ever-expanding void. This evaporation signals the ultimate conclusion of the galactic life cycle, the point at which every physical trace of the galaxy, from its brightest stars to its darkest heart, has been permanently erased from the cosmic record. This silent, uniform state is the universe's final destination, a condition known as heat death. After all the brilliant explosions and majestic mergers, the cosmos settles into a profound and permanent equilibrium. The immense temperature differences that once powered stars and galaxies have completely evened out. The universe becomes a lukewarm sea of particles, spread so thinly across the expanding void that each one is effectively alone in an unimaginable darkness. In this state, no energy can flow from one place to another because everywhere is the same. No wind blows, no stars shine, and no complex processes can occur. It is the ultimate stillness, a cosmos where time itself loses its meaning, as nothing measurable ever changes again. This is the final, inevitable conclusion dictated by the laws of thermodynamics, the point where the universe has exhausted its capacity for change and structure. Yet, even in this absolute quiet, the strange rules of quantum mechanics suggest a faint, almost impossible whisper of possibility. Across spans of time so vast they have no name, a random quantum fluctuation could theoretically conjure a new particle from the void, or in an event of unimaginable rarity, spark an entirely new Big Bang, birthing a fresh universe in a spontaneous act of creation. But these are statistical miracles in a cosmos of endless dark, not a rebirth so much as a fleeting, isolated spark in an infinite night. The heat death represents the final, complete erasure of the grand narrative that began with the first galaxy. From a searing, violent dawn to this deep, silent freeze, the life cycle of every star and every island of stars finds its ultimate resolution in this quiet, dark equilibrium. Yet the cold, silent finale of heat death is not the only possible ending written into the laws of physics. The ultimate fate of every galaxy may depend on the true and still mysterious nature of dark energy. In one dramatic alternative known as the Big Rip, dark energy does not remain constant but grows stronger over time, becoming an overwhelming phantom force. In this scenario, the accelerating expansion of the universe would not just isolate galaxies, it would systematically dismantle them. First, the cosmic glue of galaxy clusters would fail, sending individual galaxies flying apart into the void. Then, the gravitational bonds holding individual galaxies together would be overcome, tearing stars from their orbits and scattering them into the darkness. In its final, frantic moments, this phantom energy would grow so powerful that it would rip apart stars and planets, and finally, tear the very atoms that constitute matter into a spray of fundamental particles. It is an ending of ultimate disintegration where the fabric of space-time itself is shredded. Other theoretical possibilities are equally profound. Our universe might exist in a state that physicists call a false vacuum, a precarious but stable-seeming energy floor. A random quantum event could trigger a transition to a true vacuum, creating a bubble of a new, more stable universe that expands at the speed of light in all directions. This bubble would not be a place where matter or galaxies could exist. It would fundamentally rewrite the laws of physics in its wake. Every structure, every atom, every memory of a galactic life cycle would be instantly and permanently erased as this wall of new reality swept through the cosmos. There are also visions of cosmic rebirth, like the cyclic model, where the universe undergoes an endless series of expansions and contractions. In this view, a future Big Crunch would see all galaxies and all the matter they contain pulled back together in a fiery reversal of the Big Bang. This collapse might not be an end, but a reset, compressing everything into a singularity only to explode once more in a new cycle, perhaps giving rise to entirely new forms of galaxies and physical laws in the next iteration of reality. While these scenarios remain in the realm of theoretical speculation, they serve a vital purpose. They remind us that our map of cosmic evolution is still being drawn, with vast territories marked only by question marks. The final, silent fate of the galaxies we see today may be a quiet fade, or it may be something far more dramatic, a conclusion to their epic story that we have not yet even begun to imagine. Even as galaxies fade into silence, their legacy is permanently woven into the fabric of the cosmos. Their most profound gift was the transformation of a primitive universe. From that initial, uniform sea of hydrogen and helium, generations of stars within galaxies forged the entire periodic table. Every atom of carbon in a living cell, every particle of oxygen we breathe, and every fragment of iron in our blood was forged in the heart of a star and scattered into the galaxy by its death. This cosmic chemistry created the raw materials for rocky planets, vast oceans, and the complex molecules that are the foundation of life. Without this galactic scale recycling, the universe would remain a barren, simple place, incapable of building a world or nurturing a single living thing. Galaxies also shaped the very space between them. During their brilliant, active phases, the intense radiation from quasars and the collective ultraviolet light from billions of young stars kept the vast intergalactic medium ionized and transparent. This great bath of energy regulated the temperature and state of the cosmic web itself, influencing the potential for future structure formation on the largest scales. Long after a galaxy's light has vanished, its gravitational signature endures. The ripples in space-time created by the mergers of its supermassive black holes will continue to propagate across the cosmos. These gravitational waves are a permanent record of titanic events, carrying the story of ancient collisions through the void for all eternity. Perhaps the most remarkable legacy, however, is the emergence of consciousness. In at least one galaxy, on a small planet orbiting an ordinary star, the universe evolved a way to understand itself. The ability to contemplate cosmic origins, to trace the life cycle of stars, and to feel awe at the grandeur of the night sky is a direct product of the galactic environment. This cognitive awakening, this capacity for wonder and inquiry, may be the single most significant contribution of galaxies to cosmic history. Their physical forms may dissolve, but the knowledge they helped create, and the meaning we derive from their story, becomes a permanent part of the universe's narrative. We are living in a fleeting, golden moment of cosmic observation. The grand narrative of galactic life cycles, from their violent births in the early universe to their silent gravitational deaths in the far future, frames our own existence within a breathtakingly vast timeline. Our species emerged during a narrow window, long after the first stars had finished seeding the cosmos with heavy elements, yet while the universe remains vibrant enough for us to witness its majesty. We are positioned at a unique crossroads in time, able to look back and reconstruct 13.8 billion years of cosmic history, while also peering forward to predict trillions of years of future evolution. This ability to trace the life story of a galaxy is perhaps one of humanity's greatest intellectual achievements. It demonstrates that through curiosity and careful observation, we can uncover the secrets of the cosmos, turning the faint light from distant islands of stars into a coherent and epic biography. Every element essential to our existence tells a chapter of this story. The iron that carries oxygen in your blood was forged in the heart of a massive star that lived and died billions of years ago. The calcium in your bones, the oxygen you breathe, and the carbon that forms the foundation of life itself were all created in stellar furnaces and scattered across the galaxy by supernova explosions. We are not merely living in the universe, we are literal products of its galactic processes, made from the recycled ashes of long-dead stars. This profound connection ties our personal history directly to the cosmic one. To understand that our Milky Way has a life cycle of its own, that it was assembled from smaller pieces, that it has cannibalized other galaxies, and that it will one day merge with Andromeda, is to see our home not as a static backdrop, but as a dynamic character in an ongoing epic. This perspective is simultaneously humbling and empowering. It can make our individual concerns feel small against the canvas of billions of years, yet it also elevates the human capacity for wonder and understanding to something truly significant. In a universe destined for silence and cold, our brief moment of conscious awareness allows us to witness, to question, and to marvel at this majestic cosmic drama. We are the universe's way of comprehending its own story. From the first protogalaxies emerging from the cosmic dark ages to the eventual dissolution of all structures trillions of years in the future, the life cycle of galaxies represents the most grand narrative in all of existence. We have journeyed through violent births, active maturations, gradual aging, and gravitational deaths, witnessing how these cosmic islands evolve across timescales that dwarf every human era combined. This exploration reveals galaxies not as static celestial paintings, but as dynamic systems with rich histories and destinies, each one a living story intertwined with the fundamental forces of nature. They are born from quantum whispers, sculpted by collisions, stabilized by dark matter, and ultimately silenced by the relentless expansion of space itself. Every spiral arm and every elliptical swarm tells a unique tale of creation and transformation. The study of these galactic life cycles continues to challenge and expand our very understanding of physics and cosmology, pushing the boundaries of what we know about dark matter, dark energy, and the ultimate fate of reality. It forces us to reconsider our place in this vast cosmic scheme, not as central characters, but as temporary witnesses to an ongoing story that began long before us and will continue for eons after our chapter is complete. The great dance of galaxies continues unabated, and through the lens of science, we have been granted a fleeting, precious front row seat to this magnificent and humbling performance.